For section 3.5, I will not go over the slides. You can read those on your own, but it's just going to reiterate the fact that so far we've learned every single tool to take the derivative in higher order derivative of any function that looks like y equals f of x. So congratulations, this is a very important point in calculus. However, what happens if I have a function or more than one function defined for y in terms of x, in which I can't really solve for y to take the derivative? What happens then? I'm going to show you with example one that although in this case I could solve for y, it is a lot easier to find the derivative of y respect to x by using implicit differentiation. The word implicit means that in the equation you have the y variable as well, having some operations performed on them. It could be raised to the second power, it could be cubed, it could be multiplied by x. So the function, there's going to be more than one function defined for y, and it's going to be all written in the same equation. So for example, you remember that any equation in this form, x squared plus y squared equals some number squared, is the equation of a circle, and implicitly you have two functions of x here. The first function will be this portion, and from your review at the beginning of the year, you know that the equation is y equals square root of 25 minus x squared. And then you have the bottom portion of this circle, and its equation is y equals negative square root of 25 minus x squared. And you will find that result if you solve for y. And remember, when we take the square root on both sides, we generate two answers, a positive one and a negative one. So this equation, this single equation, is telling you that there are two functions. There are two f of x for all x's in the domain. So if you were to find the derivative, you will have to take the derivative of this function and then the derivative of that function, and then figure out if they have the same derivative or not. You can find that on your own. So this can be done in the regular way. You can see that there are two functions going on. First is 25 minus x squared, and then the square root is the outer function. So you will apply chain rule, and you perfectly know the root on that. So right now I just want to show you what it would be like to take the derivative respect to x for a function that is not solved for y. The only thing I want to remind you about this, let's say for example that I have, let me see, the volume of a cylinder. Okay, that's probably easy. Volume of a cylinder is given by pi radius squared times the height of the cylinder. So it is possible, since this has two variables, it is possible for me to take the derivative of the function volume respect to the radius, and it is possible for me to take the derivative of volume respect to the height, because both of them are variables in the volume equation. So the question is, would that look the same? Since volume depends on the radius, then you consider the radius to be the variable and everything else a constant. So the constant here is pi times h, and then take the derivative of the radius, which will be 2r. So let me just put the 2 in front, because that's the way that way looks pretty. So this would be the derivative of volume respect to radius. Now, taking the derivative of volume respect to height, everything else that is not height will be considered constant. So that's pi radius squared. And then the derivative of height, since the exponent is 1, then and there's no coefficient, so the derivative of h is simply 1. So this will be the derivative of volume respect to height. So notice how these two derivatives are different because on the same function you consider one of them the variable and then the others the constants. But what happens, for example, if the radius depended on the height? In this case, I have to apply the chain rule, and then there will be another factor in here. For example, if the radius depended on the height and I have a multiplication of two functions of height, I will have to apply the product rule for this. So the treatment is different when one variable depends on another variable within an equation like that. So that's the only thing I wanted to bring up. It is very important to know what depends on what. Okay, so I'm going to erase it so that it's out of the way. Okay, so this equation, x squared plus y squared equals 25. The only thing I have to remember is that y as a function of x depends on x. And this is a very important fact when I'm taking this derivative. Okay, so I'm applying the derivative to the entire equation. So derivative of x squared respect to x plus the derivative of y squared respect to x equals the derivative of 25 respect to x. Okay, notice that I can apply the derivative to the sum because by properties the derivative of a sum is the sum of the derivatives, but remember that that's not true for product and quotient. Okay, so the derivative of x squared respect to x will be 2x, and now this is where the difference is. If I'm taking the derivative of y squared respect to y, it will just simply be 2y. But I'm taking the derivative of y squared respect to x, and I have to remember y depends on x as well. So it's not simply 2y, it has to be multiplied by the derivative of y respect to x, whatever that might be. Remember that you don't know what y equals looks like you have no idea, or at least pretend that you don't have any idea. So you know that y is something something whatever x. So I'm using the chain rule. I'm taking the derivative of the outer function times the derivative of the inner function, the inner function being just simply y, and the derivative of a constant is 0. And now I'm just going to solve for dy over dx because that's what actually I'm trying to find. Solving for dy dx, I'm gonna have 2x minus 2x on the other side, and then divided by 2y. The 2's will cancel out, so I'm gonna have negative x over y, which just means the slope of the tangent line at any point will be given by this equation. So let's go back in here and let's look at what we have. This is the point 5, 0. Okay, the tangent line looks like this. Okay, that's the tangent line. So according to this, the derivative of y respect to x is the opposite of the x coordinate divided by the y coordinate. For this point, it would be negative 5 divided by 0, and you know that you cannot divide by 0, so the slope is undefined, as you know, of a vertical line. Let's look at this point right here, horizontal line. The tangent line is a horizontal line. The coordinates of that point are 0, 5, and if I replace 0 into x and 5 for y, I'm going to have the slope is 0. So it works. This is another point here where the tangent line is undefined. And then I have another point here where the tangent line is horizontal, and also the derivative is 0. Let me just show you other things that happen around the circle because they will be relevant in future functions, and since we're talking about a circle, I just want you to pay attention to some curiosities. For example, on this point, where the x and the y are the same. Okay, let's intersect the y equals x line with the circle, or you could say I'm going to solve for x. If this is x squared plus x squared equals 25, you will have x being the square root of 12.5. So let's say that this is the point 12.5 comma square root of 12.5. Oops, sorry. So if I have that point and I replace it into my derivative equation, the slope will be simply -1 because these two values will cancel out when they are dividing. So at the point where it crosses the line y equals x, the tangent line has a slope of -1. And I think it's easy to tell that by symmetry. The circle is symmetrical. It has infinite number of axis of symmetry. So definitely for -1, this is the midpoint in this arc right here. But this is not the only point that has a tangent line with a slope -1. By symmetry, this point also has a tangent line that has a slope -1. So for any value of the tangent line, there's always 2 points that have such tangent line. So if you were to find the derivative of this and derive the derivative of that, you're going to reach to the same answer, and the same derivative is for both of pieces of functions. So that's the other thing. Two different functions may have the same derivative, and that's pretty amazing. So we're going to talk about this in later sections as well. Now for part B, we have to find the equation of the tangent line at the point 3, 4. Piece of cake. The derivative of y respect to x, we found out that it was the opposite of x over y. The opposite of 3 is -3 divided by 4, and that's -3/4, and that's a beautiful fraction, and I will leave it like that. Equation of tangent line, I could use any form I want unless they specify a particular form, or if you were to see multiple choice, you have to transform it into the form that the choices are. But point slope is fine. The point is 3, 4, so it's y minus 4 equals -3/4 of x minus 3, and I'm done.